Alright, so this is going to be a quick little walkthrough of partner problem 1.11, which is entitled Brady's Leap. The problem reads in 1780 and was now referred to as Brady's Leap. Captain Sam Brady of the U.S. Continental Army escaped certain death from his enemies by running horizontally off the edge of the cliff, and of course we're changing this to a angled problem, but above Ohio's Cuyahoga River, which is confined at that spot to a gorge. He landed safely on the far side of the river. It was reported that he leapt 22 feet across while falling 20 feet. If we assume he can run up to 7 meters per second, or 15.6 miles per hour, which is doable for a human, and he jumps 30 degrees relative to the cliff, would he have enough velocity to make it across? So you can see in the top left corner of your screen, I have the picture of the setup. The picture next to that is an additional picture kind of the setup. So here's my actual setup, and then I have my additional picture, and my additional picture relates to the velocities. So for my initial setup, I converted everything from feet into meters, and I have, instead of it going 20 feet high, I have 6.1 meters, and instead of going 22 feet across, I have 6.7 meters. Now this is kind of a weird problem because it gives me the delta x, but it doesn't actually give me the delta x. So if I look here, this is the 6.7 meters. Well, that's not actually what delta x is. I'm solving for delta x, and I'm wondering if my delta x is at least 6.7 meters. All right, but we also said that he jumps at 7 meters per second. So that's right here is at 7 meters per second. But if he jumps at 30 degrees, that means he has an x component of 7 meters per second and a y component of 7 meters per second. So if I grab my calculator, well, I'm looking for the velocity in the x direction. The velocity in the x direction is adjacent to my angle, so Vx will equal V times the cosine of theta. And I'm sorry, I'm writing with my finger because I don't have my stylus. But anyway, so that's 7 times the cosine of 30. So the velocity in the x direction is 6.1 meters per second. And the velocity in the y direction will be V sine of that angle instead, because now we're adjacent. I'm sorry, opposite. So 7 times the sine of 30 degrees is going to be 3.5 meters per second. So that's where I got those two things from. All right, so I know that he's going 6.1 meters per second in the x direction, and I know that he's going 3.5 meters in the y direction. And what I'm wondering, again, is if my displacement is this 6.7 meters or not. So my equation for that is, well, this is uniform motion, because it's in the x direction. The y direction is not uniform motion, but in the x direction I have delta x equals Vx times t, and my Vx is going to be that 6.1 meters per second that I just solved for. So 6.1 meters per second, and the time. The time I don't know. And if I go back to my picture that's right up here, I'm going to kind of subdivide it a little bit. And I'm going to put these little dots here. I'm going to look at this dot across, and it might look a little dirty, but essentially I have two parts of this problem. Right here is the time that it takes for him to go up to his new height. The second part is going from the top all the way down to the ground with an initial velocity in the y direction of 0. So at first, he doesn't have an initial velocity in the y direction, but then for this, I'm sorry, he does have initial velocity in the y direction, but when I'm up here going down, he doesn't. So that's how we're going to break that problem up. So the first thing that I need to solve for is the time up. So time up, part 1 is time up. Well, I have some initial velocity in the y direction, and that equals 3.5 meters per second. My final velocity when I reach the top in the y direction is going to be 0 meters per second. So I have an initial velocity, I have a final velocity. My acceleration equals g, which is equal to negative 9.8 meters per second squared. And then I'm looking for t. So if I look at my equations, on the equations that I have, that is going to be equation number 4. And I'm just going to kind of move all this kind of stuff out of the way. And delete it. So equation 4 says that VF equals VI plus AT. Well, my VF is 0. So I'm still solving for T, so negative VI equals AT. And if I'm solving for T, I'm going to divide both sides by A. So T, and again, this is T up, equals negative VI over A. And that equals negative 3.5 meters per second divided by my acceleration due to gravity, which is negative 9.80 meters per second squared. All right, so I can plug that into my calculator. My negatives do cancel out, which is good because time can never be negative. And that gives me 0.36 seconds. So we have 0.36 seconds. So I'm going to put that back up here. I'm going to put that as my time up. So that's going to be because my total time is the time that it takes to go up and the time that it takes to go down. So I'm going to put 0.36 seconds plus, this is a decimal here, sorry. All right, well now I need to figure out my time down. And with that, I have the same problem that I had my first type of problem. And that means that the time that it takes to go down is directly dependent on my new height. And I have a special case equation that we derived today, or derived whenever we did this problem for you, and that is that the time down, so my last step is that my time down equals the square root of negative 2 times the YF all over G, and that's the square root of that. But I can't do that without knowing my new height. So I'm not ready to quite go there. But I am going to start by doing something else, and that is going to be by solving for my new height. Because once I have my new height, I can solve for the time that it took to go down. Now my new height, I have the same variables that I had before. I have my initial height, which is 6.1 meters. I'm solving for my final height. I have my initial velocity, which is 3.5 meters per second. I have my acceleration, which is negative 9.8 meters per second squared. And now, actually from before, I even have my time, which is 0.36 seconds. So I actually have a couple of options of how I'm going to solve this equation. I can use the YF equals YI plus VIT plus 1/2 AT squared. Or I can use the VF squared equals VI squared plus 2A delta Y. In either case, I'm going to solve for delta Y. I'm going to use the first choice just because I think that's a little bit neater, or a little bit easier for me, just because it gives me my height instead of my change in height. It's essentially the same thing. There's just a very subtle difference. So my equation now, I'm going to switch colors for this because this is like a side step. YF equals YI plus VIT plus 1/2 AT squared. All right. Well, my YF is what I'm solving for. I have all my variables for this actually, so it's pretty straightforward. My YI is 6.1 meters. My velocity initial in the Y direction is going to be 3.5 meters per second. My time that it took to go up is what I solved in part 1. That's going to be 0.36 seconds. And then I'm going to add 1/2. Well, my acceleration is negative 9.8 meters per second squared. And again, my time is 0.36 seconds, and that is also squared. So if I go through and I plug that into my calculator, I have 6.1 plus the quantity of 3.5 times 0.36 plus the quantity of 0.5 times negative 9.8 times 0.36 squared. And that gives me a new height of 6.7 meters. So this, looking back to my picture, that's this height right here. My new height is going to be 6.7 meters. and I'm going to solve for the time that it takes to go down those 6.7 meters. Now my initial velocity is in fact 0 in the y direction, and so I'll just get rid of this. My initial velocity is 0 in the y direction, so I can use that special case equation of t equals the square root of 2 times the initial height, or sorry, y initial, however you want to think of it, divided by g. So that's the square root of 2 times my initial height, which is 6.7 meters, divided by g, which is, sorry, that's negative 2, negative 9.80 meters per second squared. And if I plug that in, I get the square root of, well, 2 times 6.7 divided by 9.8, and I get we'll call it 1.17 seconds. So I'm going to throw that right here as well, 1.17 seconds, because that's going back into my my initial, that really initial x displacement equations, because I was, again, just solving for time. So let me go ahead and get rid of everything that does not matter, and I'll have to put that 1.17 seconds back again. Sorry, 1.17. And now I can go back to this equation right here and plug in my final time. So I have 0.36 plus 1.17, so my total time is actually 1.53 seconds, and I multiply that by 6.1 meters per second, and I get 9.33 meters. And again, I was wondering if that 9.33 was greater than my 6.7, and it is, so therefore he does successfully make the jump.